everyone, welcome to Group 3's final presentation. Our team members are Lexi Beach, Bridget O'Connor, Dylan Lyon, Luis Vargas, Miriam Taba, Nikki France, and Rita Hu. For our project, we chose to analyze a blender. As a background on the product, blenders are usually used in a variety of scenarios to mix, crush, puree, or emulsify different substances. A motor is housed in the main blender frame, which spins a shaft. The motor is driven at various speeds to provide appropriate cutting force. The shaft is coupled to the blade assembly by interlocking components. These are easily removed with the pitcher assembly for cleaning. Here is an exploited CAD to see the functional components of our chosen blender. Our target customers include the primary customer, which are home cooks who need to blend ingredients to be used in meals, and the secondary customer, which are workers in cafes and restaurants who use blenders to make foods and drinks. This fast diagram breaks down the functions desired in an optimal blender. We have two main functive branches that relate to chopping the contents while keeping them secure within the jar of the blender. Here we have our function component mapping matrix, where we map the components of the blender assembly to the leaves of the fast diagram. The leaves are the basic functions performed by each of the components. The most important components are typically those which have the most checked functions, which includes the big cap, pitcher, measuring cup, blade, and blade screw. However, some functions are more important than others, and although they are not marked often, their single function is the main part of the blender. This includes components such as the housing base, housing outer cover, and motor. This quad chart shows the functional importance of the blender components as well as their cost. As can be seen, some of the components have high functional importance but are costly, making them candidates for redesign. To begin the family design process, we started with a functional development table where we have two columns differentiating the functions for the two customer groups, restaurants and home users. Based on this table, we found that the only function that is different between customer groups is blend various size contents. Using the function component mapping matrix, we connected this functional differentiation to components. This information is presented in the component commonality table, where the modules are the components that meet the blend various size contents function. The common module for both variants will be the base of the blender, including the internal motor, buttons, and blade joints. The module will be the blade assembly, which consists of the blade itself, the blade screw, and the blade sleeve. For the secondary module, the blade assembly modified to be a longer shaft with multiple blades. This will help blend larger food sizes and quantities found in restaurants. Our product family assembly diagram consider rearranging in order which blades and electronics are added. The modified assembly sequence delays differentiation of the home blender and restaurant variants. We chose these two parts for DfA design because, according to the quad chart, both of these parts had a high functional importance but also a high cost, indicating they should be modified to decrease cost while maintaining the function of the blender. Additionally, the assembly times for each component were higher than other components, so there was the opportunity to decrease assembly time and costs.
The redesign combined the housing cover and housing outer cover. They were initially snap fit together. We added a chamfer to the bottom side of the assembly to ease insertion in the Z direction. The overall cost decreased when compared to the initial combined cost of the two separate parts. The blade module is a good candidate for redesign because it consists of 5 separate components, which increases assembly time. The redesign of the blade module flattens the blade in order to increase its symmetry. It utilizes a snap fit to reduce the number of fasteners and combines the upper and lower blade joints in order to reduce the overall part count. This allows for the function of the component to remain intact while reducing the manufacturing cost and assembly time. For automated assembly, we chose to redesign the high insertion cost parts beneath the housing mainframe. This includes a hard-to-locate motor, resist-to-fit housing lower cover, and 4 snap-fit feet. These parts are critical to blender functions and therefore cannot be removed. We made additional changes for the rubber feet and lower housing cover in order to avoid snap fits. Although this increases the number of fasteners, we found it was more beneficial overall to prioritize avoiding snap fits in this case, since there is a high failure rate during automated assembly. We also provided locating features for the motor, housing lower cover screws, and rubber feet. After our redesign, the manual assembly cost is 8.31 cents per product, and the automated assembly cost was 3.636 cents per product. This results in a 1.16 cents per product difference, which will snowball into savings much more down the line during mass production. For process selection, we chose the lower housing cover because of its critical role in housing and motor support. The critical dimensions of the housing lower cover are shown. The center hole has a 10mm diameter and tight tolerance to tightly support the motor. The width must also match the blender frame. The two valid candidate processes for the housing lower cover are die casting and machining. Most other processes fail due to the tight tolerances. We chose CNC machining as our process to save on costs associated with a die mold. Machining the original costs $5.20. The main expense was a 4mm face milling around the center boss.
The redesign of the lower housing cover used wider and fewer ventilation slots according to DfM C3 and 7. The standard size slots also replaced screw holes for fastening. The center hole's new conical bottom saved on cost for drilling as well. The redesign uses standard slot sizes to make milling simpler. Additionally, the diameter was slightly reduced to avoid resistance during insertion. We chose the upper blade joint for process selection due to its role in providing homogeneous mixing torque. The critical dimensions for the upper blade joint are its center hole for the blade screw, the pocket for blade nuts, and the outer diameter. Process selection revealed machining and injection molding were valid processes. Ultimately, injection molding was chosen for its cheaper manufacturing cost. The before upper blade joint has lots of sharp corners, no draft angles, side pulls for the torque arms, all which lead to a high injection molding cost and 1 cavity per mold. The redesigned upper blade joint transmits torque via the blade screw nuts. It adds draft angles, keeps uniform wall thicknesses, and saves heavily on surfaces and side pulls. Most importantly, the cost savings comes from eliminating the lower blade joint, which has been consolidated into this single part. The redesign changes some critical dimensions, including pockets for blade nuts, adds clearance for motor shaft and screw, and the outer diameter to sit on the other components. Comparing the two estimations for cost, analytical versus the hubs.com quote, we can see the hubs estimates a much lower cost. This is likely due to the fact that they are going to be using a casted part first and using CNC machining as a secondary finishing process. This product also provides other services for the user in order to improve their experience and reduce the impact on the environment. Recycled metals and plastics will be used during production. Blenders will also be available for rent, allowing for each product to be used by more people and reduce overall material consumption. Rentals will be accessible by app, website, and in-store. There's also a warranty that includes repair services for the benefit of the user and to reduce quantity of discarded blenders. In summary, we were able to save time and cost shown by implementing DfM guidelines, which allowed for changing the outer cover components, automated assembly parts, housing lower cover, and blade joint. Some critiques for the redesign is the need to change the housing mainframe to fit our new lower cover shape. Also using a square emboss for the new blade joint and adding complexity to the mold required to manufacture the new outer cover.